Welcome to this live Smart Learning webinar with Richard Perring. Richard is a maths teacher and maths consultant with over 14 years teaching experience. He's currently responsible for developing teaching and learning in his maths department and developing maths across the learning community. And he's also the author of our newly published Student Guide to Maths Across the Curriculum, which is a pocket-sized reference guide designed to raise mathematical levels of the curriculum. Richard's going to talk today about a plan to hand over to him now.
Cool. I think you just said you were going to hand over to me, Nicola. I have got some issues hearing you, but I'm pretty sure that I'm going on to screen share, and there's the PowerPoint. Okay. So this is a webinar about maths in science, and the idea of this is, obviously you will know that there is a huge amount of new maths content made more explicit in the new science curriculum. And so what I want to do today is just to have a look at science, maths, and a particular aspect of maths that's proportional reasoning and how that fits in with the science curriculum. So we're going to have a look at these two things. What I want to consider is the outcomes that we're expecting for our students, whether we're looking short-term, long-term. I want to think about what maths is and how you can encourage students to think more mathematically, and how you can transfer the maths that they already know from their maths classrooms into the science classroom. Because, I mean, you will know this, and I'm making assumptions, but in my experience, kids don't transfer things from one room particularly to another. And you have got a lot of science to cover, and so you will need to be piggybacking off the work of the maths department. You don't want to have to teach the kids the maths as well. You want to be piggybacking and allowing them and scaffolding them, moving from what they use in maths and in their maths lessons, taking that into the maths class, into the science classroom. This is obviously kind of a weird setup where I can't take questions. There will be an opportunity to ask questions at the end. I hope that you have a piece of paper or a pen or something, or a piece of paper and a pen would be really helpful, so that you can scribble things down, because there is going to be some work to be done and some questions to be answered. I am going to be asking you to do a bit of maths. And so the first thing I would like you to do is to have a look at this problem. And I'm going to stop for about a minute just to give you a chance to have a look at it. I just want to say that if you're seeing what I'm seeing, the key thing is that there are 3 digits and they are arranged to make a variety of numbers, and the 3 digits are different. Okay, so you've got the circle, the square, and the star. And I will now stop and give you 1 minute precisely to have a look at this. There's your minute. Okay. I don't know whether you got through. I don't know whether you got a solution or didn't get a solution. The problem is structured in such a way that it's more than just recall. It's more than just using mathematical facts. There are some mathematical facts that you need to know here. And so, for example, the key ideas here are to think that if a number is odd and divisible by 5, then it must end in a 5. If it's divisible by 5, it must end in a 0 or 5. If it's odd and divisible by 5, it must end in a 5. So we know what the star is. We know that if it's even and not divisible by 5, then we know that the square can't be a 0, because if it was even and divisible by 5, then the square would be a 0. But we don't know any more than that, except for the fact that if it's even, then the square must be a 2, 4, 6, or 8. Can't be 0. We know that the star is 5. We can work out what the square could be. We've got a range. Knowing that the next statement down, the 2-digit number circles star is divisible by 7, gives us that, well, the first number that you come to is 35. That's the first number that's divisible by 7. That ends in a 5. We know that the star must be a 5. And in fact, that's the only 2-digit number that ends in a 5 and that is divisible by 7. So we now know that the circle is 3, the star is 5, and the square is an even number but not 0. And finally, the 2-digit number square circle is prime. So this narrows it down a bit more. 23 is prime, 43 is prime, 63 isn't, and 83 is. So the square could represent 2, 4, or 8. It can't be 0 or 6. And so there's something here about using mathematical knowledge, but also there's a way of thinking. And it's that way of thinking, that mathematical way of thinking, that is exploited, and that I think is something that we miss very often when we look at maths in science. When we're looking at the transfer and the common ground between the two, we very often look at things like, when do you teach graphs, when do we teach graphs, what type of graphs do you teach? And there is an element of tying these things up. There is an element of knitting the curriculum together so that the kids' experience is sensible and that one subject builds on the other. But equally, there is more to our commonality than just the fact that science draws graphs and maths draws graphs. And there is a particular way of thinking, and I would call this mathematical thinking. It could be logical thinking, but for me that's an explicitly mathematical way of thinking. So for me, kids are doing maths if they are in the center of this Venn diagram, if they're doing mathematical thinking with mathematical knowledge. You can think and behave mathematically in different contexts. If you are, for example, preparing dinner and you sort of work backwards, you know you want to eat at 7 o'clock or whatever, so you work backwards from there. And so it's not just a case of starting this thing and then starting that thing and then putting the other. There is a sequence, and you sequence and you structure. There's an element of what I would call mathematical thinking to that. Equally, there is mathematical knowledge. I know that 7 times 8 is 56. But when I make the statement 7 times 8 is 56, I would argue that I'm not doing maths. I'm making a statement that is mathematical. But it's not. I'm not having to do maths because that's now embedded in me. That's recall. And so to be doing maths, I would suggest that you need to be doing mathematical, you need to be thinking mathematically with the stuff of maths, with mathematical knowledge. And it's those two bits that make something maths. I think that within science there is plenty of scope to develop mathematical thinking and that way of being and that way of thinking without necessarily working with mathematical stuff. I think that's kind of underexploited. And quite often, in my experience, the mathematical thinking is almost taken away. I'm thinking of formula triangles particularly, but there are plenty of opportunities where we focus on that answer, on the outcome. A sort of similar structure would be this. This is the instructions from a chemistry set. My niece got a chemistry set for Christmas. These are the instructions from my chemistry set. And I would suggest, and it's very difficult, I would very much like to talk it over, but we don't have a dialogue happening here. If you disagree, please buzz a question at the end. Or if you agree, please buzz a question at the end. So I would suggest that by doing this, this tells you precisely what to do. this instruction from the chemistry that tells you precisely what to do and tells you what you will see. You do this, you add it, the cabbage juice fizzes and gradually changes colour. You are being told what to do and being told what you will see as a result of doing that. Now, to me, that's not doing science. That's following a recipe. The second experiment that it mentions is this, and it has this added point in it. So you follow the instructions, you add 2 teaspoons of vinegar, and it says, what happens now? Now, for me, that's a really key question. What happens now allows the kids to think, it allows them to hypothesize and to question, and the problem is it then goes ahead and answers itself straight away. And so again, any thinking, any science, what I would consider to be science in this, is taken away from them because they are told what they should see, they are told what they should do, they're told what they should see as a result of that. And for me, in doing that, they're having any creativity, they're not learning the skills of science. They are learning in the same way as if we give a set of instructions in maths. They don't necessarily learn how to apply those. They follow a process. And they follow it blindly, and in doing so, we are de-skilling them from knowing when to apply something. So we need to give them both. We need to give them mathematical knowledge, and we need to allow for mathematical thinking. And so this is quite a hard balance to play, and quite often we will get rid of it. We will, our best intentions will go wrong. So this is, all right, I want you to do some maths. So just copy this down. You're going to do a takeaway, a subtraction, and you're going to do 4007, take away a number. And I'm going to reveal the number in a moment, and I'm going to give you 15 seconds, just 15 seconds, to get that number written in that gap and then do the calculation. Okay? All right, so I press that button and start at the same time. Okay, so again, I can't see what you did, but I am willing to bet I've done this question with a lot of people, and most people, when they have it, they start to do this sort of thing, and my alignment is slightly out here, I'm afraid, but by writing it out as a column, when we set this out, I'm willing to bet that a significant number of you didn't read it. You didn't read 4007 take away 3998. Most of you read 7 take away 8. You started reading from the right-hand side, and you read 7 take away 8, and you went straight into a process of, I can't do 7 take away 8, so I've got to carry. And in doing that, there's something about this way of setting out the calculation that draws in a method, that triggers an algorithm in you, or in most people that I've done this with. And particularly the more familiar you are with this algorithm, the more likely people seem to be. Math teachers fall for this all the time. The more familiar you are, the more likely you seem to be. People seem to be willing to just go for the process, which means that people aren't thinking about the question. There's not a thought here. This is a trigger. This is an instruction to act rather than a thought. So by setting it out like this, there's a question, there's a way of answering this, and we want kids to think, how am I going to do this? In the same way as in the chemistry set, we want them really to be saying, well, what am I noticing? What does happen? What might happen? We want kids to think, how am I going to do this? And most people won't do the column method with this setup, with this calculation, because it's unnecessary. And so our best intentions of setting up a calculation will often lead to kids not thinking, and we want to encourage thinking, we want to encourage mathematical thinking as well as mathematical knowledge. One of the big areas I think we do this in is graphs, and I'm not going to talk too much about graphs now. I think that what we'll do is have another one of these about graphs, because graphs is a big topic and there is a lot of commonality. And I was just looking at the program of study, and these are the graph statements for biology. Whoops. These are the statements for biology only about graphs. in the use of mathematics in the new national curriculum, and it's all over the place. But what we tend to do, I think, is because we have a short-term view, we want the kids to get the right graph in their books there and then. And so we tell them how to do it. You know, we say to them, right, you're going to draw a line graph, you're going to draw axes from here to here, you're going to space them out like this, make sure the numbers go on the lines, not in the squares, make sure you plot the points like this, label the axes in this way, title your graph, join them up, this is the type of line of best fit you're going to do, etc., etc. We give them the instructions. And then we say, God, these kids, they can't draw graphs. I have to always give them instructions. And we need to encourage this thinking from them, and we need to scaffold it. And so one of my suggestions for the way we can do this is to model the thinking through the questions. We can model the thinking that we do and the thinking that we want them to have. So we want them to think, what type of graph will represent this data well? In my experience, kids like a bar graph. I think bar graphs are easy and they're simple. And they're relatively straightforward to draw, they're familiar, so they will like a bar chart. Sometimes that will be good, sometimes it won't. But so ask them, ask the class, what type of graph are we going to use? What should we put on which axes? And what should be the scales of the axes? And then let them draw it. And if they get it wrong, they get it wrong, but they won't. We need to look beyond that one lesson or that one graph to allow them to get it wrong. Let them do it and then pull them together and compare. If you have a visualizer or a little camera in your room, fantastic, to put up a couple of graphs and discuss which one shows the best, shows the information the best, which one shows the relationship between these two bits of data the best. Ask them to make predictions and listen to their predictions and then discuss whether that's a good prediction or not. So what I'm sort of saying is, if we offer a framework rather than a set of instructions, we model the thinking, we model the skills that we want them to have, then they are more likely to be able to run through that routine themselves. If we just give them a recipe to follow, we're not going to be giving them the skills to do the maths and the mathematical thinking that we want them to do. And they should be doing, I know they should be doing this in maths, and they hopefully will be doing this in maths. But if you're doing it as well, then it will be transferring that. So one of the key things I would say is go and talk to your maths department with this list of questions and see how they do it. What would they add to this? How would they model the graph? When they're teaching graphs, how do they do it? And I think it would be very helpful to piggyback off what they do. So use their skills and use their language. And so a framework rather than a set of instructions. And so I want to look now very quickly at a framework for proportion. Because proportion, again, looking through the science curriculum, proportion is everywhere. It's disguised. It's within percentages. It's within ratios as well as direct proportion. So it's in gradients and rates. Proportion is a big idea in the maths curriculum. And in the new maths curriculum, it's been taken out of number. Before it was contained in number. Now ratio, proportion, and rates of change is a separate section. It's an explicit section within the maths curriculum. And kids need to make links. So I'm going to offer you a framework for proportion that you may or may not want to use. But there's something there about using, the idea is to give you something to show something that has a framework that kids can use to help them make connections. And so it exploits the table square. And if we take a square from the table square, such as this one, then there are relationships within this. Going from that column to that column, from 2 to 4 is doubling, and from 3 to 6 is doubling. And also going from 2 to 3 is 3 halves of 2. There's the multiplication there, and it's the same. 6 is 3 halves of 4. And so what happens to the top row happens to the bottom row. What happens to the left column happens to the right column. And so does that happen elsewhere? If we look at this square here, we've got a doubling relationship between 7 and 14 and a doubling between 8 and 16. And the same going from 7 to 8 is a multiplying by 8 sevenths, and 14 to 16 is multiplying by 8 sevenths. And so if we look at this square here, and I'm going to pause for a few seconds for you to just scribble this down and put in the multiplication, put in the multipliers. And if you do that, then hopefully you've got these. And again, the proportionality, it exploits the proportion within the multiplication square. This grid exploits that proportionality. Kids, by the way, will find this hard. They find that going from 12 to 16, the idea that you can go from 12 to 16 by multiplying very hard. The idea that you can go, if we back up a bit, the idea that you can go from 2 to 4 by doubling is fine. And even going from 2 to 3 is kind of okay because they understand the idea of 1.5. But that multiplication is quite hard when they get into more difficult numbers. And so this structure, this framework, is quite helpful for them to work with that. If we now look at a set of numbers that create a rectangle that aren't even connected, so these four corners of a rectangle, and I'm very proud of this PowerPoint, we can see that again the relationship holds. And if you need to get a calculator and check this, but this works. The relationship, the multiplicative relationship within the table square allows this to happen. So this is exploiting the structure. I guess in a similar way to the way that formula triangles exploit a particular structure within multiplication and division. And so this needs to be taught not as a gadget, but through this table square method. And so if we do that, we can look at this, which is a proportional relationship, and we can use the proportional relationship. This is now just a section of the table square, and we can use the proportional relationship within this to find that missing number. And so if we look at this, we can see that to go from 2 to 9, we need to multiply by 9 over 2. And so we could go from 5 to the missing number by multiplying by 9 over 2. Alternatively, to go from 2 to 5, we multiply by 5 over 2. And so we can exploit that relationship, the vertical relationship, to go from 9 to the missing number by multiplying that by 5 over 2. And this structure, this strategy, this framework builds on the proportionality of the table square and is a really helpful structure for working with a number of proportional situations. So I've had to go, now you will know the scientific contexts far better than I do. I've popped down a couple. The first question here, A is proportional to B when A is 2, B is 9, is a very mathematical question. That's what this is, one of the maths questions that this is answering. But it would also answer the question about an object moving at a constant speed. It could answer this thing about the ratio. It's a way of looking at this ratio, mixed in the ratio of 2 to 9. And so looking at this, it's exploiting, it's a way of structuring that relationship. And it allows kids to make connections between proportionality and ratio, between proportionality and, if we look at this one, and percentages. So we can look at percentages in this, because percentages are just another example of ratio or of proportionality. And so my suggestion is, if it's possible that your maths department use this structure. If they do, then you need to know about that so you can exploit it in order to support kids in making that connection from the maths classroom to your classroom. If they don't use this structure, then you need to find out what structure they do use, if they use a structure. And I'm willing to bet that most maths departments will have something there that says this is how we teach this particular concept, this is how we teach proportion. It might not be this, it might be something such as the bar model. And the bar model is a new, well, no, it's not that new, but it's a structure that's being used and developed quite a lot at the moment. And again, for you as science teachers, you don't want to be teaching kids how to do proportion. You need to be piggybacking off what maths are doing. So you need to find out what maths are doing. And so whether they're using this grid structure, whether they're using a bar model, what are they doing to teach proportion? What are they doing when they teach graphs? And similarly with algebra, and similarly with calculation, with other things. Find out how they're doing it, and then use a common approach. So these are my sort of suggestions, this idea of a shared framework. You don't want to tell the kids this is precisely what you're going to be doing, because then you're taking away the mathematical thinking and therefore taking away the maths. But you do want them to have a framework that's common to encourage them to make connections between science and maths. So is there a common strategy for teaching proportion? Is there an image such as the bar model? What language do they use? If you can just use the same language, the same vocabulary, then students are more likely to make those connections. And the same with pictures, with images. And again, we'll talk about algebra another time maybe. But the idea of, do they use balancing for equations? Do they use a functional machine image for equations? Do they use a bar model image for equations? Different images can be transferred, and you need to find out what they're using so that the kids can make that connection. And I think that is it. The one thing I wanted to just flag up, a lot of people don't know about this, and this is something that I stumbled across fairly recently. Talking to the maths department, having something to work together on is often quite helpful. And there's this website, compassproject.eu, and it's set up to encourage problem-solving strategies as links between maths and science. And there are some really good resources here. I've got nothing to do with the project. Smart Science has nothing to do with the project. It just strikes me that this is, if you're going to work with your maths department, having something to work on is quite helpful. And so this website has produced lesson plans and resources. There is tons of stuff here, and it's well worth a look at. So I would really suggest having a look at that, taking it to your maths department, and maybe putting something in for after September. And that is it. There is this, which might be helpful. This is the Student's Guide to Maths, which includes a lot of the images that I was talking about, such as the bar model, such as the proportion grid. And that's it. So if I now zoom back to here and stop sharing my screen, then I think that's the end. And so hopefully now we will have the opportunity to do some questions. Okay, I'm looking for questions. I think this is working now. But I can't see any questions coming up. Okay, in that case, I am going to hit the stop button. And if you need anything, if you have any questions, then if you email Smart Learning at the address that I've just got rid of here, there you go. And also, if you want to have a go at this, the ebook trial, to have a look at that. But any questions, anything you want to know, then please email here, and they will be able to pass it on to me. Thank you very much. I hope it's been useful, and hopefully I will speak to you about algebra or graphs at a later date. Okay, bye.